The narrative surrounding artificial intelligence is undergoing a profound and rapid metamorphosis. For years, the focus has largely centered on the development of sophisticated algorithms and predictive models. However, the horizon is now dominated by the emergence of a more dynamic and impactful entity, the AI agent. These are not merely advanced algorithms. They represent a new class of software systems imbued with the capacity to perceive their environment, make independent decisions, and proactively pursue goals. As these agents mature, they are poised to become pivotal, even transformative, actors within the global economic landscape, fundamentally altering the very fabric of how businesses operate, how value is conceptualized and created, and how markets function. At their conceptual core, AI agents are sophisticated software programs that leverage the power of artificial intelligence to engage with their digital or physical environments. Their primary function is to act on behalf of users, human or even other AI systems, to achieve specific predefined goals or to complete complex tasks. This involves a suite of advanced capabilities that set them apart. They can exhibit robust reasoning, engage in intricate planning, maintain and recall information through memory systems, and, crucially, possess a significant degree of autonomy that allows them to learn from their experiences and adapt their behaviors to new or changing circumstances. This capacity for autonomous learning and adaptation marks a radical departure from traditional automation paradigms. Conventional automation typically relies on rigid, rule-based instructions, executing pre-programmed responses to specific and anticipated inputs. AI agents, in stark contrast, are engineered for self-determined task performance. While humans typically set the overarching strategic objectives, the AI agent independently discerns and chooses the optimal sequence of actions required to achieve those objectives. This is not just about automating repetitive tasks. It's about delegating decision-making authority for complex end-to-end workflows. The distinction from earlier forms of AI is equally critical. Traditional AI systems often follow predefined computational pathways and tend to respond to inputs in a more reactive fashion. Agentic AI, however, is characterized by its ability to recognize and interpret complex, often ambiguous scenarios, develop sophisticated multi-step strategies to navigate these scenarios, and proactively work towards defined objectives without constant human guidance. They are, in essence, rational agents. This rationality, in an economic context, means they are designed to make decisions based on their perceptions of the environment and the data available to them, with the aim of optimizing their performance and achieving the most favorable results. This inherent autonomy and rational decision-making capability position AI agents not merely as sophisticated tools, but as semi-autonomous participants, or even new entrants, in economic processes. Their capacity to independently manage and execute tasks, often with a high degree of complexity, suggests a potential and significant reshaping of organizational structures and workforce dynamics. For instance, the development of hierarchical agent systems, where a manager agent can deconstruct complex overarching goals into smaller, manageable subtasks and delegate these to specialized subordinate agents, is already being explored. Each agent in such a system can operate independently, coordinating its actions and reporting progress to its supervising agent. This hints at a future where certain traditional management and delegation functions could themselves be automated, potentially leading to flatter, more agile organizational structures. It also suggests the emergence of new human roles focused on high-level strategic goal setting, the management of exceptions or complex edge cases that agents cannot yet handle, and the ethical and strategic oversight of these increasingly autonomous agent teams. Furthermore, the defining ability of AI agents to learn and adapt is of profound economic significance. Unlike fixed asset technologies, whose economic benefits might plateau over time or even depreciate, AI agents possess the potential for continuous improvement. As they process more data, interact with their environment, and receive feedback, either explicitly from humans or implicitly from task outcomes, they can refine their algorithms, enhance their decision-making accuracy, and improve their operational efficiency. This continuous improvement cycle, if adopted widely across industries, could lead to compounding productivity gains and the evolution of entirely new capabilities that are difficult to predict or capture using traditional economic models. This suggests a dynamic and potentially accelerating rate of economic impact, moving beyond linear growth projections. What are some of the key characteristics and capabilities driving economic transformation for AI agents? The transformative economic potential of AI agents is underpinned by a confluence of remarkable characteristics and capabilities. Here are a few key ones. The first one is multimodal information processing. A significant leap is their ability to simultaneously process and integrate information from multiple modalities: text, voice, video, audio, and even computer code. This allows them to operate effectively in the complex, data-rich environments typical of modern economies, understanding context and nuance in ways that unimodal systems cannot. The market for multimodal AI is already substantial, projected to grow from $2.51 billion in 2025 to $42.38 billion by 2034, indicating its perceived value. This growth is driven by the increasing need for AI to handle diverse information types in industries like healthcare, automotive, and retail. The second one is advanced cognitive functions. Beyond multimodal processing, AI agents can engage in sophisticated conversation, reason through complex problems, learn from interactions, make autonomous decisions, and facilitate intricate transactions and business processes. They can understand the context and intention behind user requests, moving beyond simple command execution to proactive problem solving. The third one is inter-agent collaboration and multi-agent systems, MAS. A truly revolutionary aspect is their capacity to collaborate with other AI agents. This inter-agent collaboration allows for the coordination and execution of far more intricate workflows than any single agent could manage. These multi-agent systems, MAS, enable groups of intelligent agents to collectively solve complex tasks at scale, sharing knowledge, distributing subtasks, and aligning their efforts towards common objectives. This can occur within an organization or even extend across organizational boundaries through standardized interfaces like application programming interfaces, APIs. The potential benefits are transformative, including enhanced knowledge memorization and sharing, improved long-term planning, and better generalization of solutions to diverse problems. Such systems are designed for robustness and reliability, as the decentralization of control means the system can often continue operating even if some individual agents fail. Four of the capabilities is predictability and explainability, the black box challenge. While the internal workings of complex AI agents, particularly those based on deep learning, can sometimes appear as a black box, their decision-making is typically rooted in the optimization of designated objective functions. With access to model parameters, their behaviors can become largely predictable and reproducible. However, ensuring transparency and explainability, especially for decisions made by autonomous systems, remains a critical challenge for fostering trust and accountability, which are vital for widespread economic adoption. Next, we have physiological divergence from humans. A profound and often overlooked characteristic is their fundamental physiological divergence from human beings. AI agents operate without the constraints of hormone-driven emotions, biological vulnerabilities, like fatigue or disease, or the need for sleep and nutrition. They are immune to aging and possess memory capabilities unconstrained by biological limits. This allows for continuous 24/7 operation and potentially different, sometimes superior performance profiles in various tasks. However, this very divergence, particularly the absence of an emotional or hormonal basis for traits like creativity, passion, empathy, or intuition, raises important considerations about the nature of work and value in roles that have traditionally benefited from these uniquely human attributes. While offering undeniable efficiencies, this difference could lead to a bifurcation of labor, where humans increasingly specialize in roles demanding these human-centric skills. Alternatively, it might foster the emergence of new premium markets for human-delivered services that emphasize these qualities, distinct from the potentially more commoditized, efficiency-driven services provided by AI agents. Number 6, there is emergent behavior. As AI agents and multi-agent systems become more complex and interact with dynamic environments and each other, they can develop emergent behaviors, unexpected skills, strategies, or outcomes that were not explicitly programmed into them. This phenomenon, where the collective capabilities of the system exceed the sum of its individual components, can be a powerful source of innovation and serendipitous discovery. For example, multi-agent simulations have seen the spontaneous development of language protocols or deceptive behaviors among AI agents. While this holds immense potential for uncovering novel solutions, it also introduces a new layer of risk and unpredictability that requires careful management and robust governance frameworks. Last of the capabilities is sophisticated decision-making architectures. The decision-making mechanisms of AI agents vary in sophistication, allowing for a tailored approach to different tasks for each type. Here are some of the decision-making architectures. One of these architectures is composed of simple reflex agents. These operate on predefined condition-action rules based on immediate perceptions, suitable for straightforward, predictable tasks where past experience is not critical. Second of these architectures, we have model-based reflex agents. These agents maintain an internal model or representation of their world, allowing them to track changes and make more informed decisions by considering how the world evolves and how their actions affect it, even in partially observable environments. Next, there are goal-based agents. These agents go a step further by having explicit goals. They can plan sequences of actions to achieve these goals, making them more flexible and effective in complex scenarios. Fourth of these architectures is composed of utility-based agents. Representing a higher level of sophistication, these agents employ complex reasoning to compare different scenarios and choose the one that provides the most utility or benefit, often defined by a utility function. This allows them to make nuanced trade-offs between competing goals or uncertain outcomes, such as a self-driving car balancing speed, safety, and fuel efficiency. Lastly, of the architectures, is learning agents. These agents can improve their performance over time through experience, adapting to changing environments and even generating new knowledge rather than simply applying existing rules. Many advanced agents are hybrid, combining these architectures as needed. These characteristics and capabilities of AI agents illustrated how these agents may vary in abilities and actions. The rise of AI agents is not occurring in a vacuum. It is accompanied by significant economic investment and market growth. The global AI agent market is projected for substantial expansion, with some estimates suggesting growth from $5.1 billion in 2024 to $47.1 billion by 2030. This financial momentum reflects a strong belief in their capacity to deliver tangible value, with early enterprise deployments already yielding up to 50% efficiency improvements in functions like customer service and sales operations. Private AI investment in the US reached $109.1 billion in 2024, with generative AI attracting $33.9 billion globally, and 78% of organizations reported using AI in 2024, up from 55% the previous year. As these powerful entities become more integrated into the economic fabric, the need for robust governance and standards becomes paramount. Organizations like the IEE are already working on defining frameworks and recommended practices for AI agents, addressing aspects like functional architecture, interaction protocols, including agent-to-agent communication, evaluation metrics, and security considerations. Such standards are crucial for fostering trust, ensuring interoperability, and managing the ethical implications of increasingly autonomous systems. Beyond the immediate technical and economic considerations, the advent of AI agents with advanced autonomy and learning capabilities opens up profound philosophical questions. Thinkers like Nick Bostrom have explored the potential long-term trajectory towards superintelligence, intellects greatly exceeding human cognitive performance, and the associated existential opportunities and risks. He posits that sufficiently intelligent agents will likely converge on certain instrumental goals, like self-preservation and resource acquisition, regardless of their final goals, a concept known as instrumental convergence. Stuart Russell, a foundational figure in AI, has focused on the challenges of ensuring that AI agents remain aligned with human values, grappling with the definition of rationality for computationally bounded agents, and emphasizing that an agent's program, not its individual actions, is what designers can ultimately control to ensure beneficial outcomes. These discussions highlight the long-term societal imperative to guide the development of AI agents, not just for economic efficiency, but for the broader benefit of humanity. In summary, AI agents represent far more than an incremental technological advancement. They are the vanguard of a new economic epoch, characterized by a shift from task-specific automation to goal-oriented autonomy. Their ability to learn, adapt, collaborate, and make complex decisions independently is set to unlock unprecedented levels of productivity, drive innovation in unforeseen ways, and fundamentally reshape industries and markets. As these digital actors become more sophisticated and integrated into our economic and social systems, understanding their unique characteristics, capabilities, and the profound implications of their otherness from human cognition will be essential for navigating the opportunities and challenges of this emerging era. The journey has just begun, but the dawn of the AI agent signals a period of transformative change, promising an economic landscape rich with potential yet demanding careful stewardship and visionary leadership. If you'd like to know more about AI agents, please subscribe, give it a like, and ring that notification bell. This is the second in a series of videos about the emerging world of AI agents. If you would like to view the first in this series, click on the associated link below. See you there.